Hello everyone, good morning to all. Welcome to Sciacademy channel. You will be learning here in this video lecture about the mechanical properties of solids, and this is related to chapter 9 class 11th. फ्रेंड्स, आप लोग जो है इस वीडियो लेक्चर में मैकेनिकल प्रॉपर्टीज ऑफ सॉलिड्स के बारे में पढ़ेंगे, जिसमें हम लोग डिफरेंट टॉपिक्स डिस्कस करेंगे. So let's start the video lecture. So firstly we will introduce ourselves about the mechanical properties of solids, elastic behavior of solids, stress and strain, Hooke's law, stress strain curve, and various elastic moduli. So under introduction, already you have the knowledge about the solids and rigid bodies. So what are the solids? Solid क्या है? So आप लोग को सबको पता होगा solids क्या है. Solid जो है जिसका जो है एक definite shape and size होता है, and solids is very rigid to be modified, compressed and bent. But not all solids are that much rigid. So solids and rigid bodies are two things. Solids may be rigid, may not be rigid. So a solid body has a definite shape and size, and in order to change or deform it, a force, external force is required. And after applying this external force, when we remove the external force, body generally restore its initial forms. Like if you stretch a helical spring, that means if you are taking a spring like this, and if you try to stretch by applying the two opposite tensile forces, then it will be stretched, and after removing the external force, the spring will come back to its original shape. The property of a body by virtue of which it tends to regain its original size and shape when the applied force is removed is known as elasticity. So elasticity is the property of the body, and it is inherent property of the body. ये बॉडी के अंदर होती है और उसका ही एक कैरेक्टरिस्टिक्स है, जिसकी वजह से बॉडी क्या होती है, अपने इनिशियल शेप में रिस्टोर होती है जैसे ही हम जो है एक्सटर्नल फोर्स को हटा देते हैं. एंड when we remove the deform force means the force which is applied externally, body restore its position, and if we apply much external force, there is a possibility that the body gets deformed permanently, and this property of the substance is known as plasticity. And when the body is restore its initial position, then that body is known as elastic body. So there are two things, elastic and plastic. Similarly, there are corresponding elasticity and plasticity. Plasticity, for example, if we take some mud and apply some external force, so mud may be deformed for the permanently, and it may not gain its original shape and size. Therefore, the mud is close to the ideal plastic. The elastic behavior of material plays an important role in engineering and design. For example, while designing a building, knowledge of elastic properties of materials like steel, concrete, iron, etc. is essential. And this type of knowledge must also be required to design bridges, automobiles, aeroplanes, ropeways, etc. So, if we are asked, can you design an aeroplane which is very light but sufficiently strong? So, what type of material you will choose? So, you will think about the properties of the solids material that is strong enough to sustain the load, as well as you will think about the weight of the material. So, if you have proper knowledge about the material, then only you can design an aircraft of the required properties. Similarly, when we talk about the artificial limb, the limb should be light as well as strong enough to sustain the weight of the body of the person. So for that, you must be known that we take the material like carbon fibers and carbon nanotubes, which are stronger and lightweight simultaneously. So that means for designing such type of things, you must have the knowledge about the properties of the material. Okay. Also, shape of the body is important. For example, when we design a railway track, we take a particular shape like I for the railway track so that it may bear the load of the train. Similarly, you know that glass is brittle while brass or other solid material like iron, steel is not. So answer may be given by studying the mechanical properties of such material like elastic behavior. So let us discuss about the elastic behavior of solids. You know that each atom or molecule, for example, let us consider here the NaCl substance, that is the table salt, and you may have noticed here the arrangement of the atoms or ions of the chloride and sodium. They are arranged in a standard format, standard fashion, order fashion. They are arranged in a regular systematic manner. You can see here one chloride, then sodium, then chloride, here, then sodium, then chloride. They are ordered and they are attached together by a bond, ionic bond, and this ionic bond provides the connection between the two ions, and they are so strong that they make the NaCl compound stable, and such type of bond is known as ionic bonds, and they are attached together by the forces known as interatomic forces or intermolecular forces. When a solid is deformed, the atoms or molecules are displaced from the equilibrium positions, and this is because a change in the atomic, interatomic or intermolecular distances. So when we apply the external force, so what will happen? There is a change in the interatomic distances between the atoms, ions, and when we remove the external force, what will happen? They will, that means the atomic ions will try to come into the initial position because of the interatomic or intermolecular force of attraction. Thus, the body regains its original shape and size. The restoring mechanism also can be visualized by the spring ball model. Here you can see that balls are attached together by a systems of springs. So each balls are connected together by the spring. Here if we assume the ball as atoms and spring as the interatomic forces, then if you try to displace any balls from its equilibrium position, what will happen? The spring system tries to restore the ball back into its original position. Thus, friends, elastic behavior of solids can be explained in terms of microscopic nature of the solids. So, if we talk about the elastic behavior of the solids, then you must think of the solids in terms of the macroscopic level, how the ions or molecules of the solids are arranged on the a- atomic level or molecular level. Only then you can realize the restoring capacity of the solids after removing the external forces. And if you want to realize or visualize the how the interatomic forces acts, this is the spring ball model is the best example for your visualization. There were many scientists who tried to explain the elasticity of the solids, and one of them was the Robert Hooke, who tried to explain the elasticity behavior of the solids, and in the honor of him there is a Hooke's law. We will study about the Hooke's law. Before that, we must know about the what is strain and what is stress. So let us discuss about the stress. What is stress? When forces are applied on a body in such a manner that the body is still in static equilibrium. So condition is that after applying the external forces, body should be in static equilibrium. And when we apply the external force, the body gets deformed to a small or large extent, extent depending on how much the external force is, as well as the nature of the material of the body. So that means, so deformation depends upon two things. What? The amount of or magnitude of external force applied and the nature of the material of the body. Nature of the material of body, right? So deformation depends on two things: magnitude of the external force as well as the nature of the material body. The deformation may not be noticeable visually in many materials like steel, but it is always there because deformation may be very very small, so that it is difficult to visualize the change in the body. When a body is subjected to a deforming force, a restoring force is developed in the body. That means if we try to deform any body by applying the external force, then the body will try to restore its shape after removing the external force, and this restoring force is equal in magnitude but opposite in direction to the applied force. So there will be the restoring force. So restoring force is equal and opposite to the applied force. Therefore, restoring force per unit area of cross section of the body applied where the external force is applied is known as stress. That means stress is nothing but the force applied per unit area of cross section. Okay, this is the magnitude of the stress, and if F is the applied force and A is the area of cross section, then this stress can be given by the formula stress is equal to F by A. Now the SI unit of the stress can be given by Newton per meter square or Pascal, and its dimensional formula you can write as the ml minus 1 T minus 2. So this is the dimensional formula of the stress. Now there are three methods in which a solid may be deformed according to its dimensions. So that under that condition we have three types of stress. First is longitudinal stress, second is shearing stress, and third is hydraulic stress. So we will first understand one by one these three stresses: longitudinal stress, shearing stress, and hydraulic stress. So friend, when we apply the force, suppose we are talking about this figure, when we apply the force perpendicular to the cross section of the area. So if we are taking a cylinder, this is a cylinder, and we are applying this force like this, and that is the perpendicular to the area of this cross section. In that case, this restoring force developed per unit area is called tensile stress. So if A is the area of cross section of this cylinder, then in this case when the applied force is perpendicular to the tensile stress, then this sorry perpendicular to the area of cross section, then this is called tensile stress. And we can also visualize that if we are compressing this cylinder inside, then then also force is perpendicular to this area of cross section, and in that case we call the compressive stress. Compressive stress. That means these two, tensile stress and compressive stress, are nothing but the longitudinal stress. So longitudinal stress, when the applied force is perpendicular to the area of cross section, then we call the restoring force per unit area as the longitudinal stress. Friends, you know that when we are applying the force on a particular body, then this force will change its shape or size. So suppose the length of this cylinder initially was L, and after applying the external force outward to this cylinder perpendicular to the area of cross section, then there is the extension delta L. That means there is an increase in the length of the cylinder delta L. Then the ratio delta L to the initial length of the cylinder is known as the longitudinal strain. Okay, so this strain is along the force, and that's why it is called the longitudinal strain, and it has no unit. You can visualize here that delta L is having the same unit as the L, so ratio of the delta L and L will have no unit, therefore strain has no unit or dimension. Okay, sometimes it is asked in the exam, what is the unit of strain? So you must remember that because the strain is a ratio of change in the length to the original length, therefore it has no unit. Now let us suppose the case 2. Here two opposite forces are applied, but here the forces are along the area of the cross section. Because of that, there is deformation in this cylinder, right? But that is in different form. There is relative displacement between the opposite faces of the cylinder. So initially the faces of the cylinder were opposite to each other, and, and just like this. But when we applied the two opposite forces parallel to this area of cross section, then there is a relative shift towards this, and this relative shift between the opposite faces of the cylinder causes the shearing strain and the restoring force per unit area developed due to the applied tangential force is known as tangential or shearing stress. So here we have tangential stress or shearing stress, and this stress is developed only when we are applying the opposite parallel forces parallel to the area of cross section, right? And there is, here you can notice that there is shift of the this opposite faces related to each other by delta x, and this delta x can be expressed, this change or shift can be expressed in terms of strain that is known as shearing strain, and it is defined as the ratio of relative displacement to the length of the cylinder, and this is shearing strain, and this is nothing but the tan theta. You can see here, this is the angle theta, and this makes the right angle triangle, right? So with this we can have the tan theta is equal to delta x by L, and that is nothing but the shearing strain. If theta is very small, in that case we can write tan theta is nearly equal to theta. Therefore, theta is equal to delta x by L, and that is the shearing strain. So, friends, you must remember this relationship, because based on this relation, numerical problems are asked, and आप लोग को इस बात का ध्यान रखना चाहिए जब आप फिजिक्स पढ़ते हैं तो न्यूमेरिकल प्रॉब्लम्स बहुत इंपॉर्टेंट होता है, और न्यूमेरिकल प्रॉब्लम्स जो है फिजिक्स का जो है बेस है, और न्यूमेरिकल प्रॉब्लम्स को सॉल्व करने के लिए आप लोगों को कंसेप्ट क्लियर होने चाहिए, फार्मूला याद रहना चाहिए. सो यू मस्ट रिमेंबर दिस फार्मूला. Shearing strain is equal to delta x by L, that is equal to theta or tan theta depending upon the theta's value. Now we up to now we discussed the longitudinal stress, longitudinal strain, shearing stress, shearing strain. Now let us take the third type of stress, that is hydraulic stress. And when we put a solid sphere, suppose we are considering this figure, suppose this is a pond and we are putting the sphere inside this. So what will happen? There will be pressure from all sides to the sphere, and because of this pressure on the sphere, there may be change in the volume of the sphere, and this change and pressure is known as the hydraulic pressure. Pressure or hydraulic stress, the force applied by the fluid acts in perpendicular direction at each point of the surface of the sphere, and under this condition, this sphere or any body placed into this liquid or pond is said to be under hydraulic compression. So, hydraulic compression is because of the fluid pressure, and that acts always perpendicular to the every point of the body. And because of this hydraulic compression, there is change or decrease in the volume without any change of its geometrical shape. So you must notice this. If forces are acting from all sides, then there is a decrease in the volume, but but there is no change in the geometrical shape of the body or the sphere, what we consider here. Only there is a decrease in the volume, but no geometrical shape change. But as the inherent properties of the body develops internal restoring forces that are equal and opposite to the forces applied by the fluid. So the body restores its original shape and size when taken out from the liquid. The internal restoring forces per unit area in this case is known as the hydraulic stress. Okay, so this is the restoring force per unit area when we consider the case of fluid, and its magnitude is equal to the hydraulic pressure, and that is the applied force per unit area. Therefore, hydraulic stress is nothing but the hydraulic pressure. So that pressure is nothing but force per unit area. And in this case, volume strain, that is the volume strain, because there is a change in the volume here, is given by the change in volume to the initial volume or original volume. And again, it has no unit or dimension. It is a dimensionless quantity. So strain is always a dimensionless quantity. Friends, I hope that you are able to understand this lecture. कोई डाउट्स हो, कुछ प्रॉब्लम हो तो जरूर हमें बताएं. So now we'll talk about the Hooke's law. So what is Hooke's law? Hooke's law is given by the Hooke, Robert Hooke, who was the English scientist, and in the honor of his name, this law is given, Hooke's law. So Hooke's law is very important, and you must remember that this is the empirical law. Empirical law means there is no theory derived for this law. This law is purely based on the experiment and observation. Okay, so let us discuss what is Hooke's law. Strain and stress take different forms. As we discussed earlier, that is longitudinal stress, shearing stress, hydraulic stress, right? For small deformation, the stress and strain are proportional to each other. So condition is that the deformation should be small. Deformation should be small. That means there is some limit of deformation beyond which the body will not be elastic. So we'll study about those things. So when the deformation is small, it is in the limit, then stress and strain are proportional to each other. That means stress is proportional to strain, and if we take the equality, then there will be the proportionality constant. That means stress is equal to K into strain. So K is nothing but the proportionality constant and is known as the modulus of elasticity. Because this is empirical law, so therefore there are most of the bodies or material which follow the Hooke's law, but few are also there which do not show or exhibit this relationship. So, so let us discuss about the stress strain curve. What is this stress strain curve? So this curve is based on the Hooke's law. Let us discuss this in detail. So you know that the stress and strain depends on the two things: the amount of the force applied as well as the material of the body. And the relationship between the stress and the strain for a given material under the tensile stress can be experimentally studied. And when we studied the stress strain relationship for a given material, then we found this type of curve, and this curve is stress strain curve, and this is for a typical material. The fractional change in the length, that is the strain, and the applied force needed to cause the strain is plotted. That means if we plot the strain along x-axis and stress along y-axis, then for the certain range, that is this 0 to a, that is, suppose this is point O, so OA, the stress strain curve follows the linear path. that is proportionality is being respected, and as we increase the stress beyond this point, the linearity, the proportionality is not being followed, and this stress strain curve vary from material to material, and this curve help us curve if we increase the stress, that means force per unit area, beyond this point in the region A to B, stress and strain are not now proportional. So the stress and strain proportionality is not valid for the region A to B. In spite of that, body returns to its original dimension after the load is removed. That means in the region A to B, restoring capacity of the body is present. That means when we remove the external force, the body restores its original dimension. But the linearity and the proportionality relationship between the stress and strain is not followed for this region A to B. And the point B in this curve is known as the yield point, and it is also the elastic limit. That means this value of stress is the limit for this metal, beyond which the elasticity is not restored, and this corresponding stress related to this point B is known as the yield strength. We denote this stress related to this corresponding yield point as sigma y, and this is known as the yield strength. Okay, and it is particular for the particular material. Now further, if we increase the load, the stress developed exceeds the yield strength and strain increases rapidly. So you can notice here that for small change here to here, for a small change in the stress, there is a large change in the strain. That means for the small increase in the stress beyond this yield strength, there is a larger change in the strain. The portion of this curve between B and D, this is just C is a particular point, any random point, but after this small change in this stress, the change in the strain is larger, and this portion between B and D can be visualized when the load is removed. Suppose at point C, then the body does not regain its original dimension. That means anywhere, if you consider this point C here, are here, the body is not going to restore. So for the sake of this example, if we take this C here, this point C is known as the permanent set. That means even the stress is zero, the strain is not zero. The material is said to be have a permanent set, and the deformation is said to be plastic deformation. And the point D, this D is known as the ultimate point, and corresponding to this point, the stress is known as the ultimate tensile strength. So this is the ultimate tensile strength. Okay. And in this case, after this point B and before point D, means B to D, the body is plastic in nature. Okay. So friends, I hope that you are understanding this. If any problem, please ask me in comment and join this lecture as soon as possible. This ultimate tensile strength is denoted by sigma U, and this is also particular for the particular material. Beyond this point D, a additional strain is produced even by a reduced applied force, and fractures occurs at point E. So this point E is the fracture point, and after D there is no need of uh, external force. That means if small, you have already applied enough stress, and even if you are reducing the stress, then there is also a change in the strain. That means body is going to the next level, that is it becomes fractured, and this point E is known as the fracture point. If the ultimate strength and the fracture points are close, so depending upon this distance D and E, we categorize the body into two types. What are the two types? First, brittle material. Third is the ductile material. So if the distance between D and E, that means point D, that means the point of ultimate tensile and the fracture point are very close. In that case, the body is known as brittle. That means the body material is so brittle, means it will break, fracture very soon. And if the distance D and E is larger, then it sustains some more stress, and in that case the material is known as ductile. Therefore, stress strain behavior varies from material to material, as already I have discussed this. For example, if you take rubber, it can be pulled to several times its original length. So if you are taking a rubber string, suppose you are taking a rubber string, this is the initial value. But this rubber string can be stretched to many times. It can be stretched to up to this limit. right? But if we are taking some material like iron, so it cannot be stretched many times. It may break after certain point, fracture after certain point. That means different materials have different limits, right? So it is asked in the various exams about the brittle and ductile material, and you can correlate this brittlity and ductility of the material with the ultimate point and ultimate tensile strength, fracture point, right? So it can be asked that which will be less for the D and which one less D and E for the brittle or ductile. So you should be able to give the answer that if the distance between D and E, जब D और E का डिस्टेंस कम होगा, उस केस में जो है मटेरियल जो है जल्दी से ब्रिटल हो जाएगा, ब्रेक हो जाएगा, फ्रैक्चर हो जाएगा। और यदि D और E का डिस्टेंस ज्यादा है तो उस केस में मटेरियल जो है डक्टाइल होगा, जैसे आपका गोल्ड है, सिल्वर है। तो क्या है, ये मटेरियल को जो है हम लोग जो है बाय अप्लाइंग द फोर्स वी कैन मेक ए थिन शीट, they are highly ductile material. In that case, gold and silver, the D and E are very large, distance are very large. So that means their gold is gold is able to be expanded in a sheet form because of its ductility nature, right? Now let us some consider the case of elastic tissue of the heart. So I discussed that different materials have the different stress strain curve, but the elastic tissue of the aorta doesn't follow the Hooke's law. Similarly, rubber also, and such type of material is known as elastomers. What is name? Elastomers, right? So this is the typical example of the stress strain curve for the elastic tissue of the aorta of our body. You can see here that it is by applying the stress, this is following the exponential path. That means it is not follow the proportionality relationship between stress and strain. That means elastic region is very large, right? The material does not obey the Hooke's law over most of the region. So that's why it is known as the elastomers. So friends, this is for now. I will continue this lecture. I will discuss the elastic moduli and other properties in the next video lecture. Till then, you take care and continue this video and subscribe the Sciacademy channel so that you can watch this video lecture on time and press the bell icon to get the notification of the upcoming videos. Different elastic moduli such as Young's modulus, shear modulus, and bulk modulus. So we'll start with this stress strain curve. Here we already discussed about the region of proportionality. This O to A is the region where the material follow the Hooke's law, that is, stress is directly proportional to strain, and this region of stress strain curve is of great importance for structural and manufacturing engineering designs. Stress and strain is a constant, and this is the characteristic of the material, and it is known as modulus of elasticity. So this modulus of elasticity is the characteristic of the material, and we must have the prior knowledge of the modulus of elasticity of any material before using it in the construction or manufacturing of any designs. So this modulus of elasticity is of three kinds. First, Young's modulus. Second, shear modulus. And third, bulk modulus. So let us first discuss the Young's modulus. What is Young's modulus? So as per the experimental observation, it is found that the magnitude of the strain produced is same whether the stress is tensile or compressive. That means for longitudinal stress, strain is same for a given material. That means the ratio of the stress by strain what type of stress? So this stress is longitudinal stress, and we denote it as sigma, and this strain is the longitudinal strain. We denote it as epsilon. So this ratio is known as Young's modulus, and we denote it as Y. So we found that Young's modulus Y is equal to sigma by epsilon. This ratio is of much importance, and it has the dimension of Newton per meter square, and its dimensional formula is ml-1 t-2. As strain is a unitless, dimensionless quantity. Further, since we know that longitudinal stress sigma can be written as the force per unit area, and epsilon, that is the longitudinal strain, can be written as the ratio of the change in length to the initial length of the body. This gives that Young's modulus Y can be represented as F by A divided by delta L by L, which gives Young's modulus Y is equal to F cross L divided by A into delta L. So this is the relationship for the Young's modulus, and its dimension is same as that of the stress. Now, friends, if you have any doubt, please ask me in the comment or chat. Now, it is the value, it gives the value different for different materials, and you can see in this table that for the aluminum it has 70, and for steel it is 200, and for glass it is 65. That means the material which has high Young's modulus is more elastic. So elastic doesn't mean that it is more extensible or more expandable. Elasticity means it is the capacity or ability of the material to restore itself after deforming force is removed. How fast the restoring capability is determine the elastic property of the material. So if you are asked, generally it is asked in the examination or test also, that if you are given a steel ball and rubber ball, and you are asked that which one is more elastic. So generally students used to tell that rubber ball is more elastic. So it is not like that. Ball or rubber can be stretched multiple times of its initial size, that is elastomers, but steel is actually more elastic because it has the more restoring capability than the rubber. That's why its Young's modulus is higher than the other material in the given table. Because of this reason, steel is preferred in heavy-duty machines and structural designs. Other materials such as wood, bone, polystyrene, have small Young's modulus, you can see here, and are used for other purposes. So friends, it is of importance that before using any material, one must have the knowledge of the Young's modulus. You can see that in case of steel, the ultimate strength is 400 Newton, 400 into 10 to the power 6 Newton per meter square, and yield strength for this is the 250 into 10 to the power 6 Newton per meter square, which is highest among the material given in this table. So now we will discuss the determination of Young's modulus of the material for determination of Young's modulus of the material of a wire. So for that, experimentally we want to determine the Young's modulus of any material of a wire. For that, there is a setup for the determination of Young's modulus of the material. Here, two wires, one is known as reference wire and other is a wire of which we want to know the Young's modulus. So both wire is hanged from the stable base plate. Okay, and in the reference wire, a meter scale, main scale is attached, and in the experimental wire of which we want to know the Young's modulus value, a vernier scale is attached. Initially, the small weight is attached to both of the wire so that they can stretch downwards and remain under a tensile stress. As we increase the weight of the wire, the tensile stress starts increasing, and for every increase in the length of the experimental wire corresponding to the increase in the weight, we note it. Okay, so you must have doubt or query that why we are using the reference wire, because we can do this experiment by single wire experimental wire. Why we are using the reference wire? So reference wire is used for the compensation. In the compensation, if there is a increase in temperature of the wire, it may get elongation. So if there are two wires, one wire is a reference wire, so corresponding increase in length due to the temperature can be noted, and accordingly the increase in length of the experimental wire can be adjusted, compensated. Okay, now let R and L be the initial radius and the length of the experimental wire. Therefore, area of cross section can be given by pi r square. Now let m be the mass that produced an elongation delta L in the wire. Thus, applied force in this case will be equal to m into g, where g is the acceleration due to gravity, and this applied force acting downwards. Okay, because of this applied force, there is a change in the length of the wire delta L. Therefore, Young's modulus can be calculated as y is equal to sigma by epsilon, where sigma is the longitudinal stress and epsilon is the longitudinal strain. And here longitudinal stress is mg divided by the area of the cross section pi r square divided by delta L by L, which gives that y is equal to m g into L by pi r square into delta L. So by this formula, we can get the Young's modulus of this wire, and we can repeat this experiment 3 times and take the average of the 3 readings to get the more accurate value of the Young's modulus of the wire. So friends, I hope that you understood the concept of Young's modulus. It is nothing but the ratio of the longitudinal stress and longitudinal strain, and how we can calculate the Young's modulus of any wire experimentally. So let us proceed further. Now we will discuss about the shear modulus. What is shear modulus? So shear modulus is also a ratio, and it is defined as the ratio of shearing stress divided by the shearing strain. We have already discussed about the shearing stress and shearing strain. So this shear modulus is denoted by capital G. Therefore, shearing stress sigma S divided by shearing strain now shearing stress is nothing but the force per unit area. Therefore, F by A divided by shearing strain, that is given by theta is equal to delta x by L. Therefore, this delta x by L. After simplification, this capital G becomes F by A into L by delta x. In another terms, you can also write the shear modulus as G is equal to F by A by theta. So this gives G is equal to F by A into theta. So there are two forms for the shear modulus, and these two forms can be utilized in calculating the numerical in solving the numerical problems, because numerical problems may be asked in different forms, may be given the delta x, may be given the theta. So therefore note it down and be prepared for the numerical problems. Now further, since theta since this also gives G is equal to sigma s by shearing stress theta. So shearing stress can also be calculated in terms of the shearing modulus into shearing stress, shearing strain. So this is another formula for the shearing stress and shearing strain in terms of the shear modulus. Okay. Further, the SI unit of shearing modulus is same as of the other moduli, like that is Newton per meter square, as shearing strain doesn't have any unit or dimension. This shearing modulus is also known as modulus of rigidity. So modulus of rigidity or shearing modulus are the same thing. Friends, the numerical problem based on these concepts I will solve in the next lecture. Till then, you revise these concepts and remember the formula. Now we will discuss the various shearing modulus of rigidity for the different material. You know that shearing modulus or modulus of rigidity is also different for different material. Like for iron, it is 70. For aluminum, it is 25. For copper, it is 42. And for nickel, it is 77. For steel, it is 84. And for tungsten, it is 150. And for wood, it is 10 only. So shearing modulus or modulus of rigidity, you can see that it is highest for the tungsten, and after that it is for the steel, and then nickel, and then iron. So these are the modulus of rigidity for the different material. Now let us discuss the bulk modulus. So bulk modulus is related to the hydraulic pressure, hydraulic stress, and hydraulic strain. So now let us define the bulk modulus. It is again a ratio of the hydraulic stress to the hydraulic strain, and it is known as the bulk modulus B. So bulk modulus is always given as B is equal to minus P divided by delta V by V. Here delta V is negative. That means when we apply the external pressure, there is decrease in the volume. So ultimately, this formula gives the positive value for the bulk modulus always. So negative sign here indicates that the fact that with an increase in pressure or decrease in volume occurs. That is, if P is positive, if you are increasing the pressure, there is a decrease in volume. That volume is negative. That means P and V are delta V are in opposite sign. Thus, for a system in equilibrium, the value of bulk modulus is always positive. Correct? Got it? So, for positive P, there is negative V, delta V, and resultant B will be always positive, and SI unit of this bulk modulus is same as that of pressure, that is Newton per meter square. So this is also Pascal. Now the reciprocal of the bulk modulus is called the compressibility. So compressibility is also a term which is defined as the reciprocal of the bulk modulus, and it is denoted by K. K is equal to 1 by B. So this compressibility is equal to 1 by B, and it can be expressed in terms of pressure and volume as 1 minus 1 by delta P. Sorry, minus 1 by delta P into delta V by V, because we are taking the reverse of the reciprocal of the this bulk modulus. Therefore, we get this value K is equal to minus 1 by delta P into delta V by V. Okay. So you can see that from the table, this table, that bulk moduli for solids are much larger than the liquids and gases. So these are the bulk modulus of different materials, and these are for the liquids and gases. So you can see here for the bulk modulus is low for liquids and very less for the gases. That means it requires much pressure for changing the volume of these materials, solid materials, and it takes less pressure for changing the volume of the liquids and gases accordingly. Thus, solids are the least compressible, and whereas gases are the most compressible. Why it happens? Why there is a large B bulk moduli for the solids and less for the liquid and gases? This is because the in solid in solids the attraction between the atoms or molecules are strongest. They are highly strongly bonded together, and therefore to deform them it requires large pressure or large force, external force per unit area. The incompressibility of solids is primarily due to the tight coupling between the neighboring atoms. The molecules in liquid, on the other hand, are less bound with their neighbors, but not as strong as in solids. Therefore, for the liquids, is higher and compressibility is bulk modulus is low and compressibility is higher in comparison to the solids. For the solids, bulk modulus is high and compressibility is low. Okay, now I stop this video lecture here, and I hope that you understood today's video lecture based on the mechanical properties of the solids, and you will revise this concept and we'll solve the numerical problems based on these concepts in the next video lecture, and we will cover the rest of this chapter in the next video lecture. Till then, take care, and if you have not subscribed the Sciacademy channel, please subscribe it so that you can get the updation on the time, and this may be your contribution to us so that we can get motivated. We will be in a high to provide you the best video lecture and you will get benefited.